in methods, we know that, well, I guess in methods, we're normally used to just, if you have a single population, like let's say here, let's say this is just A. If you have a single population, then you can straight away just get like your mean to just be some value and your standard deviation. Oh shit, all right, this is the correct notation. And we know that standard deviation will just be like sigma or something, right? That's what we normally know. And we know how to calculate just normal probabilities just for a single population. But let's say you had a combination of two different ones. So let's say you have a population from Australia and you had one from America. So what if you combine the two together and you created a whole new one, a whole new sample containing of both Australia and America? Well, the probability it doesn't change too much, actually, in terms of finding your mean and your standard deviation. You have these two formulas that these are also in your formula sheet. And it's as simple as this. So let's say you had let's see. Yeah, so if you had two variables, let's say x1 and x2. So if you were to get let's say we had the combination of the two. Well, your mean of e to the x1 plus e to the x, if you had the e to the x of x1 plus x2, this is the same as just e to the x1 plus e to the x2. And similarly, well, okay, yeah, I can go this way. And so, and here as well as, if you had a population, let's say you had this population of Australia, let's say, and instead you make it twice as large. Let's say this is like twice as large of Australia. So this is, let's say 1, but this one we times by 2. So you have a larger population in reality. Let's say you wanted to get the mean of this sample. So you have e to the, let's say, Australia. So if you had normally just Australia by itself, like scale of 1, then let's say your mean is just mu. Let's say mu is 0. But if you were to get the expected value of 2 times by Australia, well, with our properties of the mean, this is actually the same as just 2 times by e of Australia, which is just equal to 2 mu 0. And one last property is that, let's say you increased it with I believe it's called a location parameter. So if you have Australia and then let's say you added, let's say 8. Well, this is basically the same as just e of Australia and then just plus 8. Really simple stuff. And for variance, however, it's a bit different. So if you had, actually, I'll just write it like this. I'll write it in full general form. Or in a full general form. So let's say in general, these are basically the two formulas you realistically follow. So if e to the a of x plus b. So given that, given that x is your independent variable. Well, if you have e to the ax plus b, well, this is just the same as a times by e to the x plus b. So basically, this a just comes out, and you can just add the b as normal. So pretty much like similar properties there. And these all have their own proofs. So you can just look in the textbook. I'm not going to bother putting the whole thing down because there's a fair bit. Then you have variance. So if you had variance of ax plus b, this is actually equal to a squared times by the variance of just x. So this additional constant gets completely removed, and your constant comes to the front and is squared. And so you get this here. These are really the only two things you have to know. Because these kind of, I think those are the only two is really required. Nothing too much about that one. But then there's something new that comes up with is just well, actually, I'll quickly give an example. So let's say you have a variable x, an independent variable x. Let's say your mean was 5 and your standard deviation was, let's say, 3. Well, if you had e to the 5x plus 1, well, that's equal to 5 times by e to the x plus 1, which is the same as 5 times by 5 plus 1, which is just 26. And if you want to get the variance similarly, this is just 5 squared times by variance of x, which is 25, times by variance of x, which is, now remember, this is standard deviation. We're looking at variance, so 3 squared, which is 9. And they'll equal, let's see, 225. Oh, yeah, that's just your variance. So if you just, let's say you want to find your standard deviation of 5x plus 1, then you get the square root, which is just 15. I think, yeah, that's really the main basis of independent variables. Let's see. Oh, and okay, I'll probably introduce one more small thing, one more small combination that is also needed. So let's say you have one variable of, let's say you had mean of 5 and a standard deviation of 3. Okay, same thing. But instead you had y, which has 4 and a standard deviation of 1. So actually, I should probably list this before. Actually, you know, yeah, I haven't. I'll quickly go through that here. If you had like more than one combination of an independent variable, well, it's what you can. They're pretty much the same thing, really. Like you can split it essentially. If you have an addition of 2, you can split it. So similarly, if I had e to the, let's say, ax1 plus bx2, this is just the same as e to the a of x1 plus e to the b of x2. So you can just simplify this further, and you have this right here. And with variance, pretty much the same thing. You can just split it. You just split it. And so here you would get variance of a x1 plus, write this correctly, plus variance of b x2. And that's just the same as x squared or variance of x1 plus b squared or variance of x2. And so, and that's for that thing. And really common as well, these kind of independent variable questions, and you have to really note what is happening, because for certain questions you realize that it's not as what you think it is. And I'll probably show, I think there is some textbook questions out there. I'll probably try and find one. Actually, I can choose this question right here in a bit. I think, yeah, that really is the main basis of everything. And not only that as well, you can also have combinations with your independent variable. Instead of being discrete, you can make it also in like a completely, so the data can just be fully normally distributed, right? So like if you have x to be, let's say it's normally distributed to have, well, I'll go for the same example. Why not? I think that's what I had. That's whatever. So now let's say if I wanted to get e to the, let's say 5x plus 1. Now we have, I'll go back to my last year. I'll make it the same thing as I had before. Right here. So you have this here, you have 26. And I'll say quickly standard deviation of 5x plus 3, which is equal to 15. And so, oh, I just realized this is meant to be 1. Okay, then I did have 1. Okay, I'll just quickly change that real quick. It should be 1, 1, and 1. And so something like if this data was able to be normally distributed. So let's say like if x is normally distributed, then whatever you add on to here, so ax plus b is also normally distributed similarly. And that's really the main basis of it. So here, let's say if I wanted to find the probability that, let's say 5x plus 1 was to be more than 0. Well, I found this is basically the same as, I think if I write it in proper form, and yep, so we have a mean of 26 and a variance of 225, given the probability of 5x plus 1 is more than 0. And you can just put this into CAS and get whatever answer. And even some questions as well, they might give you as let's say you have a variable of y, which is equal to 3x plus 1. Then you would have to say, well, if you want to find probability that y was to be, well, I guess same thing, more than 0, but then this is the same as probability that 3x plus 1 is more than 0. And if you wanted to as well, you could also do something like you could switch terms around. So you have probability of 3x to be more than -1. But I don't think you can divide both sides by -3 straight away, because I believe it does cause some problems in which I've had in the past, but I'll have a quick check on that one. But yeah, normally what you would do is if you want to look at the probability of 3x plus 1, given that, let's say y or x is normally distributed, and then you just do the same thing and apply this whole idea into here. Pretty simple stuff there. And I'll give a quick question. I'll probably put a quick time limit on it too. So let's say this is from 15a. Question 15. Okay. So let's say, so you have Mickey here. Actually, I don't even have to write the name. Okay. So let's say you buy, okay, so you have 3 bags of bananas and 2 bags of apples. So let's see, the bananas are actually I'll put it like this. So both the bag of bananas let me see, yeah. A mean weight of 750. Also 750 and a mean weight of 1,000. Let's see. Variance of 25 and 50, respectively. And so, and here I'll say, I'll put in another color. Find the mean and standard deviation of the purchase. So I'll quickly put it this way: if you buy 3 bags of bananas and 2 bags of apples, both the bag of bananas and the bag of apples are normally distributed with a mean weight of 750 and 1,000 and a variance of 25 and 50 respectively. So find the mean and standard deviation of the purchase. I'll probably quick timer on it too. Let's see. I'll just put a small timer. Let's say, give you like so you're buying 3 bags of bananas and 2 bags of apples. And so you have bananas and apples being normally distributed with a mean weight of 750 and 1,000 and a variance of 25 and 50 respectively. Okay. So I'll just write this information down. So let's say for bananas, I'll say you have 3 times it. And so your bananas are, your banana has a mean weight of 750 and a variance. Actually, I'll put it this way. I'll say sigma squared. And let's say you had apples. So we have 2 bags of apples. And so your mean weight is 1,000 and your variance would be 50. I'm going to have the solutions on me as well, just to make sure. Just quickly get that up. I kind of lost my way. Just 1 second. 50. Okay. Yeah. So now, so if I put it this way, so let's say, just to make this easier, let's say we'll let P equal 3B plus 2A. So like P would be her purchase, basically. So now we're looking for the mean and standard deviation. So expected, the mean of the purchase would be the expected value of 3B plus 2A, which is same as 3 times B, which is 750. Oh, sorry. Plus 2 times A, which is 2,000. Let me add that up and let me just check my solutions. I'll have a quick check. 15. This should give you 4,250 grams. I'll have a quick check on my CAS just to make sure. Now, if we wanted to get standard deviation, so if we want to get standard deviation, well, first we need to get the variance first, because standard deviation doesn't have its own properties, only variance does. So first we get the variance of P, which is equal to variance of 3 of, okay, I can't write, B plus 2 of A. That's the same as, well, variance of 3B plus variance of 2A. This is the same as 9, remember, because 3 squared times by variance of B, plus 4 times by variance of A. Now, variance of B is, let's see, 25. So 9 times 25, that's, let me see, 250, so 225. Plus, now the variance of A, let's see, variance of A is 50, so 50 times 4 is 200. So your overall variance is 425. So therefore, your standard deviation of P should be the square root of that. And that will give you 5 root 17. Let's check that. And that is pretty much it. Actually, I'm going to quickly check that. Did I do anything wrong? So that's fine. Yep, 9 times variance, which is variance of maybe that's not, I think that this should be right. I'm not sure why the solution is saying something else. Maybe I messed up somewhere. At least if I write the question right, let's see, 25. Let's see, 25, 750, 51,000, okay. Not sure if I read any part of the question wrong, I hope not. I think this should be fine, but I mean, you guys get the whole gist of it. That's basically it. I'll give one more question as well that will be much more, okay, yeah, I'll give this one. I'll actually take a screenshot and do this one. So let me quickly connect my display. Just quickly get this up. Let's see how long this will take you. Let's say 2 minutes and 30 seconds. Let me check real quickly. This should have been, I'll quickly list which question this was from. This was from 15, let's see. Yeah, so this would have been 15B in the Special 3-4 textbook. Okay. So your independent variables of x and y each have a normal distribution. So your x has a mean of 10, and your y has a mean of 12. Then they have standard deviations of 4 and 3 respectively. So this would have been 3, this would have been 4. Okay, when I was doing this textbook question, I got really stuck as well. So if your probability of x is less than y, this really does not make any sense at all when you look at it, but there's a really simple fix to this, and you literally just minus y from both sides, and there you go. This is your new variable. So now let's look at x minus y as a variable. So let's get e to the, the expected value of it. So the mean of x is 10 minus 12, which is -2. Now we want to get standard deviation. So first we get the variance. This one's something you need to be careful of a lot as well. So firstly, these standard deviations will be, I'll write it this way. This is actually the variance of x plus variance of -y. So, and so this is 1 squared, which is just, so let's say variance of x, which would be 9, plus this -1 does not matter at all because it's going to be squared anyway. So it will be plus 16, which is equal to 25. So your standard deviation of x minus y is equal to 5. Now it's just a matter of putting these two into your cas and solving for probability that this has to be less than 0. So I'll quickly chuck that in as well, if I have it. Okay, here we go. So we're looking at less than 0. So upper bound is 0. The mean would be -2 and standard deviation is 5. I think this is actually no, it can work, I guess. So 15b9. Yep, this is the answer again. So if you look at probability that x is x minus y is less than 0, you should get 0.6554. Check if you do have that. Let me quickly just get rid of this. Yep. Combinations is that we have combinations of independent variables, but instead of having the population, you will have samples. So let's say you even have one whole sample here. You have 2 whole samples here. Sorry, the samples populations. And so you choose to get a sample. Let's say, I'll say this is A dash, and this one to be B dash. And so what happens if you were to get a sample? Actually, no, that's wrong, because that's not actually covered. What actually it is, how'd you get, let's see, how'd you get 0.6554 from the workout above? Okay, so if you want to know, so do you understand how I got the expected value and the standard deviation? Yeah, okay, so what you should have done is if you found the probability that x minus y is less than 0, well, x minus y as a whole variable, what you should have put in your cas is you're looking at normal distribution, because these are all normally distributed. So, so your mean is -2. Your variance would be 25. Well, when you write it and you're working out, you normally have to put variance, but in your cas, put in the actual standard deviation, obviously, given that your probability that x minus y should be less than 0. So what you should have had is, let's say upper bound, lower bound, mean, standard deviation. This is meant to be cas, by the way. Like, just want to let you know. So upper bound would have been 0, your lower bound would have been -infinity. So your mean would have been -2, and your standard deviation would have been 5. Put this onto your cas, you should get 0.6554. Check if you do get that. Yeah, all right, all goods. So now the one more thing is just, let's say you were to get a combination of these two, you get one whole thing of A plus B. But instead you decide to get a sample of this. And it's literally just normal sampling. Like there really is nothing else for me to do. You guys know that, well, if you had a normal sample, if you have a sample, this is the same as the original thing divided by the number of the word's not funny to me. I guess the number of like things in the sample. And that's really it. Let's see if I can do let me have a quick look at the textbook, see if I needed to explain a bit more than that. Let's see. Oh, well, actually, I need to go over this thing as well. So there's a small thing called the sample mean. It basically means that, well, we know in like normal sampling, so like if you have a certain sample and that okay, so population here, you take out the sample, and this sample happens to be the, like let's say here your mean becomes, so let's say you're measuring height. And so the mean of the entire population is like, let's say 161 centimeters. Well, then obviously when it comes to your normal sample, or when it comes to your sample, it is also the same. But if you go here, and let's say you get a standard deviation, well, if you get your standard deviation as, let's say, 5 centimeters, well, when it comes to your sample, there's actually a formula for this as well, and it's actually for your sample. I think it is the same as the methods formula, but this is the simplified version, and it's basically a sigma divided by root n. And so in this case, it would actually just be 5 over root n, given n is your sample size. That is a formula I would quickly put in here. So if you have e to the x, like let's say x is your population. Let's say this is equal to mu, then x bar, which basically means like a sample. So this would be sample. Well, this is also the same as mu, same thing. But if you have, actually I'll write it this way. So if you have standard deviation of x, which is equal to, let's say sigma, well, the standard deviation of your sample would just be sigma divided by root n. And I'm pretty sure this is a simplified version of the formula in the methods one, where it's, I believe it's like this. So p times 1 minus p over n. I believe it is the same thing, but it's just much more simplified here. Doesn't come to me the proof straight away, but I'll just leave it at that. I recommend keeping this for special, not methods, but I'll go on. I'll do someone else. Okay, no, that's fine. Yeah. So yeah, these two formulas you do want to keep in mind right here, this one and this one. I mean, pretty simple stuff. This is also in your formula sheet. Let me just quickly check that. The way they write it, let me just have a quick check what they put. Yeah, pretty much everything is the same thing. So like, actually, I'll take a screenshot of it and I'll put it here. This is what you have in your formula sheet, and so it's best to remember it, obviously, but you don't exactly have to. There you go. So this is in your formula sheet completely. So here you have the properties that we talked about earlier, right here. Those are the variance and expected value properties. Those are for random variables, but it also applies for independent variables as well. Oh no, sorry, this actually only applies for random variables. I don't know what I'm talking about. Yeah, this only applies to random variables here. But for independent variables, it is a different story, and I will go through it in a bit. Let's see. Independent random, let me have a think. Oh no, they are the same thing, I believe. Yeah, no. They are the same thing, but there's one thing that I do need to make sure of, that I'll go through. I'll give a question because it is really important. But let's say, well, this is all the same thing. So here, like if your confidence interval given your mean, well, this is the same thing in methods as well. It's basically mean plus or minus z times the standard deviation, right? This standard deviation is nothing, just this square rooted. And this is the same z value, and this is just your sample mean. Sample mean. That's really all there is to it. That's really all the formulas you need. That's all I can think of at the top of my head. So I'll give another question because, and there's one certain type of question I'm looking for because it is very important. Let me see if I can find a good one. Let's see, time. Okay, not really needed. Okay, you know what? I'll go through the one last thing. I think there is one last thing I need to talk about. Yeah, so there's that I need to talk about, and doesn't really come up. I'll give it anyway. Yeah, sure. All right, so quickly go into I'll cover quickly the last two small things, and then I'll give you like some questions to do. So if you're 15E and let me have a quick check. Yeah, so so there's one small theorem I'll quickly talk about. I've been doing some small practice papers, and I've had it come up twice. Well, not that what the actual theorem is, but you kind of have to refer to it to make it to make the question work. So basically, like this mainly refers to only sampling, and so if you do get a sample size of, let's say, 3, and you're looking at okay, so let's say you're measuring height, you're measuring the height, and so you have 3 sets of data. You get let's say 161, 150, and let's say you get like 140. Pretty simple stuff. Well, now if you draw a graph here, actually I'll quickly put in one more just to make it make sense. Now if I want to draw it, let me remember quickly. Is it the history graph? I think it's a bar graph, just a normal one. But let's say you had 140 here, 150 here, and 160 here. So now 140, you would let's say this is like frequency. This would be frequency. This is just height. So here you would have 140 only appears once, and 150 appears twice, and 160 appears only once. Now you can't, like, this is all discrete probability. So this is all a discrete distribution, but you can't really tell, like, you can't really estimate what it would be like if, let's say you had one here of 145, or here you had something of 153. It's kind of hard to determine what it would be like based off that. But something you notice is that if you want to keep increasing your sample size, so let's say your mean here was 150. Now let's go back here and you have a mean of 50. Well, actually, if you calculate this, your mean should be around, should be 50. It might be a little bit off, but it should be 50. I'll put this as 160 just to make the numbers nice. I'll have a quick check. Okay, yeah. So your mean here is 150, and so this is your mean here. But you can't really see anything much here. You can't really see much here. But if I were to increase the sample size, now let's say you have 150, and you go even more like in detail. You have 152, 153. Actually, I'll put it this way. So yeah, 150 or 140. Okay, is a bit better. Here you have 140. Here you have 150. Here you have 160. I drew these as bar graphs. I'm going to replace that actually, because this is actually wrong, like logically. What this should be is this discrete data, which is like that. It should be just a straight line with a dot. I'll quickly draw that here. That is what actually is happening, right? And you can't really tell anything if it's 145, 153. That makes more sense. Yeah, my bad for the bars. But here, let's say you get a range of values. So let's say your range, so let's say you have 1, so that's a razor. This is 1, this is 2, this is 3. So let's say your mean was 150. And so you get a mean, and more of your data will be around here. So let's say you build more, get more blocks here. So like in between, let's say here was 153, well then that will match up to here, which is 1. Something you start to notice is as you I really can't speak. As you increase the sample size, well, the graph kind of looks like this here. And so this theorem is basically it's basically called central limit theorem. I'll write it down actually. Central limit theorem. What it basically says that as you increase n, so let's say n goes to infinity, then your discrete data is approximately like normally distributed, and that should make sense as well. It should make sense because as you if you want to keep increasing it, well, maybe your data might be more like this, more like here, and it starts to become more of a normal distribution, right? So if you get more accurate results, like let's say you look at 150.1, then you get even more detailed results, and you'll slowly get something like a normal distribution curve. And that makes sense as well, because at the peak, it shouldn't rest at where the mean is. And obviously the mean being like what you expect, the expected value. That's where majority of your outcomes will be. It will eventually just become like a bell curve. So that's why if you increase your sample size, the larger it is, the more approximate it is to a normally distributed data. That's the basis of central limit theorem. Yeah, so like, actually, I'll reword that. If you have a sample, well, actually, no, that's all fine. Let's see. Oh, and I should quickly mention that so with this as well, you have your e to the x, x bar will equal the mean, this being the population one, and your standard deviation of the sample will be sigma divided by root n. I'll quickly write that too. That is really the main basis of central limit theorem. In the textbook, they say that for most distributions, a sample size of 30 is sufficient, but it definitely depends on what the situation is and how accurate you want your data and your results to be. Let's see if I can give a quick question. Okay, let's see. That's not really. Oh, actually, no, I have a question prepared. Okay, so I'll actually leave this later. Another small detail I'll quickly cover. This is already covered in methods. I'm not going to get too much in there, but if you have a confidence interval, of a sample, then you have your sample mean minus z times y sigma, and this one plus z of sigma. But I should quickly mention that for a sample, it should be sigma divided by root n because you're looking at a sample, nothing else. That's already methods knowledge, so I'm not going to go too much in depth because you already do methods, so this will already be known. Yeah, okay. Let's see what else. There is one more thing they have, and it's called margin of error. Now, I haven't seen this at all, even in VCAR papers as well. But I'll go through it anyway. What it basically means is it is the it's basically the distance from your sample mean to the endpoints of an interval. Admittedly, I should have done more study on this because I really can't think of like too much about the logic. But let's say like you have a normal distribution like this. Let's say here, this whole area would be your 90%. Well, let's say this is I drew this badly. Actually, I redo this. So let's say you have this here. Looks a bit better, somewhat more symmetrical. So let's say at these points, I'll make this easier. Let's say z is equal to 2, z is equal to -2. So this should be, let me get this right, 95%. And so basis here is that you're looking for, so here would be your mean is equal to 0, and your margin of error is just this distance here. And if you think about it, well, in your confidence interval, you normally add or subtract a certain value, and that is basically your distance. That is actually what it is. So your margin of error, that is literally equal to z times y sigma over root n. Yeah, that's it really. And so if it was 95%, well, we know that z has to equal 1.96. So it'll just be this times y sigma over root n. Yeah, that really is it. I have not seen anything in, yeah, I haven't seen this kind of thing in questions, but who knows if it will come up in the next VCAR exam or something. Okay, so I'll quickly have, get a question up, let's see. Let's see. Oh, actually, I'll give you this kind of question too. So this will involve confidence intervals. So this will have a bit of, this is basically methods knowledge, if anything. But these kind of questions come up very often and it's in probability. So I'll quickly go through it. Or I'll quickly give you this question to try, see how you go with this one. Let's see. It's pretty big. Okay. It works. Yeah, I'll give you about, let's say, how long will this take? Let's go 3 minutes. Go for 3 minutes, see how you guys go with this one. Involves some methods questions, but this will also have, these questions are directed to some methods as well. Like you can use some methods knowledge, but a lot of this you also have is some special knowledge. So I'll give you this to do, and I'll probably time you about let's say 5 minutes for this one. My apologies for the previous question, but there's this question right here. Try this one. It shouldn't be too bad. Yeah. These questions. I did realize I did make a mistake in one of the. I'm gonna come back to it from one of the textbook questions. I just realized I need to come back. Anyway, so Ln is there's a normal distribution of a mean of 30 minutes, and standard deviation of 5 minutes. And we'll school in 30 days. Okay, I don't think that matters too much. Yeah. So final probability the average time is this. Okay. I will probably say, so let's say A equal Alan's walking time. So we're looking at the probability that A is less than 28. So just simple, you can just put this straight into your CAS. 4 decimal places, 0.0142 should be our answer. I am looking at this because I've done these questions prior to this, so I'm just looking at what I did. And I checked these as well, so these are fine. So we have a 95% confidence interval for the time it takes for Alan to walk to school. Okay, so we know for a 95% confidence interval, Z must equal 1.96. So therefore, our confidence interval would be the mean minus Z of sigma, and the mean plus Z of sigma. See, we don't have some kind of sample, so our mean doesn't change at all. This is basically just a methods question, really. So the mean here is 30 minus 1.96 times by the standard deviation of 5. Could do that again. 30 plus 1.96 times by 5. And so you get your confidence interval as 28 point. Oh, well, that's very wrong. Hang on 1 second. Did I do something?
No.
Yo.
Can't you just put this into the CAS?
Yeah, you can. You can put it into the CAS.
Okay.
Yeah. This is all CAS questions, you know.
Nah, I couldn't tell.
Okay. So, oh, sorry. No. I think I did just read the question wrong. Let me have a quick check. I did read the question wrong. Okay. Yeah. Okay. So average time is 10. So have a quick check. Walks to school. I don't think they specified it well here. Yeah, I don't think they specified it well here. But let me see if they word it well here. It says average time in general. Okay. Here, the time it takes for Alan to walk to school. Okay, yeah. No, that makes sense. So a key detail that you may have missed is that Alan walks to school on 30 days. So if he walks to school on 30 days, so here is looking for the time it takes for Alan to walk to school. And so what it's basically asking is, what's the confidence interval for 5 root 30. It should be 5 divided by root 30. Remember, because sigma divided by root n for a sample. Sorry, did you put divided by? No, my bad. I didn't see that. No, you're right. I completely messed that up. Let me see. Yeah. It would be 5 divided by root 30. And this would also be 5 divided by root 30. I didn't read the question properly, but it basically, if Alan is walking to school on one day, then, out of the 30 days, he's walking on one day. So out of 30 days as a sample, then you're looking at what the interval will be for when it's walking to school. So you do get 28.21 to 31.79. This is all CAS questions, by the way. So I hope you knew that. And here you look at the time it takes. So first you have a new person. So you have Linda normally distributed with a mean of 25 and a standard deviation of 4. Assuming the walking times of Alan and Belinda are independent, okay? Is it leave at the same time? Find the probability that Alan arrives to school before Linda. So I'll quickly say we'll let B equal Linda's walking time. So what we're looking at is pretty much the probability that, let's see, Alan arrives to school before Linda. So A is less than B. That's really what we're looking at here. And so here you find in, so now actually on my paper, well, I think it's the same thing still. Let's see. Okay, no, that still works. So here you take one to the other side. I decided to do B minus A to be more than 0. So I took that as one variable. You can take the other way. You should get the same answer because of the symmetry. B minus A. So I got the expected value, which is -5. And then the standard deviation of B minus A, which is root 41. So now we look at the probability that B minus A is more than 0. And you should get 0.2174. That shouldn't be too bad. Okay. Have a quick check if I had more questions below.
Wait, what did you put in your CAS for the first part?
First?
Yeah.
Let's see. Find out the average time is less than 28. I believe your standard deviation should be 5 divided by root 30. That's probably why.
Oh, that makes sense. Yeah.
Yeah, but looking at the average time it takes. Actually, let me see. Yeah, average time it takes. These average times, yeah. If you look at average time, if you think about it, like if you walk for 30 days, well, on average, how much time it takes to walk. I should have specified that earlier. That's my apologies. But if you're looking at the average time it takes, well, you're looking at the average of all 30 days. So that's why your sigma here will do that. I'll write the whole your mean here should have been, let me check, 30. And your standard deviation should have been 5 over root 30. So you look at probability when A is less than 28. Should probably write that down. But let me check my CAS. This should be the right answer, if I'm not wrong. Yep, that's about right. Yep. Yep, that's about it. So do you want me to cover hypothesis testing now, or do you want me to cover it next lesson or something? Quickly check if I have more questions I can use. That's hype testing. That's also hype testing. That is hype testing. Okay, I actually didn't prepare any other. Okay, I'll quickly get some from the. That's why I was wrong. Yeah, I was being completely stupid here. Let me quickly go over this because this is important. So, okay, there's 2 types of things you can get. You can get either, I should have specified this before. I don't know why it didn't come to me. So either they can have, the questions can ask you like this. So they can probably define a variable to be like y is equal to 3x plus 1, or they can have it independent. And that's why my answer was actually wrong. I'll quickly go through it actually. So right here, I said that, well, if you have 3 bags of bananas and 2 bags of apples, well, if your variables are independent, they all have their own individual independent things. So if I say if you have 3 bags of bananas, you'll have 1 bag of banana here and a different bag and then another bag. And then you have 1 bag of apple and another bag of apple. And all of these are independent variables because they don't rely on each other, right? If you have two bags of apples, well, each bag are not going to rely on each other. They're all separate. And so this is also why I got the right answer luckily but I've technically it was wrong. What this expected value is should have been this. It would have been B1 plus B2 plus B3 plus A1 plus A2. I should have specified that much earlier. I don't know why it didn't come to me straight away. That is why. And so that's actually why that I got, well, if you use your expected value properties, well, this is the same thing as e to the e times by B1 plus 2 times by expected value of A1. So that's why you still get the same answer as 4250. But when it comes to variance, though, variance is a different story. So this whole thing in general is just wrong. This notation. Yeah, definitely try not to stick to it. I did just then, and I completely messed up. Yeah, you shouldn't rely on that because that can really mess it up. That's my apologies. That's completely my bad. Because what this variation actually is, it would be again as stated, B1 plus B2 plus B3 plus A1 plus A2. So when it comes to variance, it's actually just variance of B1 plus variance of B2, and so on. Oops. Yeah. So what's actually happening here, the difference here? Well, in this case here, I drew here. So if I have y is equal to 3x plus 1, well, in this case, it doesn't come to me straight away what kind of realistic situation is happening. But it basically is I'll put it this way. You have one variable that's completely dependent on another variable. So you have y is equal to, well, one variable, and maybe they have like a scalar and then some sort of locational parameter. And so that's why one variable can be dependent on those two. Or you have the other situation where each individual one are independent of each other. I should have definitely specified that. That's my apologies. And so here, well, each bag has the same variance, but they're all independent of each other. And so, well, the variance would just be 3 times by, 25. Yeah, plus 2 times by 50. That gives you 7,500, so 275. So standard deviation will be the square root of it. I'll say standard deviation actually just by itself. Let me just quickly check if that's the proper. I believe that should be the proper answer. Okay, maybe I just did something wrong with my working. But I mean, yeah, I think 275, let's see. Yeah, that is about right. I'm not sure why the solutions are slightly different, but it should be this. So yeah, I completely messed up because each of the bags are independent of each other completely. They don't depend on each other at all. Their weights or their weights don't depend on each other. So that's why I was clear wrong. That's my bad. And you'll actually see that in more questions that I messed up in a previous question about that. I'm gonna quickly let's see if I can get a different question. Let me just VCOD 2019. So all independent variables, so that's where you have to do like x1 plus x2, etc. Here's one of those questions where you they already define how the variable differs and based off like other variables. So yeah, so quickly here, yeah, x and y being independent variables, each having a mean and a variance. Wait, so each have a mean of 4 and 9. Okay, yeah. So they both have a mean and variance of 9. Okay, so this z in general has a mean of 8 and a variance of 90. Okay, so we get e to z, well, that will equal a times the expected value of x, which is 4a, plus the expected value of y, which is 4b. Yeah, that is right. That should equal to 8. So we write a plus b is equal to 2. Just to simplify that. Then you have variance of z. So variance of 9. Yeah, this is the both of a variance of 9. So that'll be 81. No, 81, sorry. It should be okay. Let's see. You have 9a squared plus 9b squared should equal 90. So you get a squared plus b squared, which is equal to 10. Yeah. That's also why they give you possible values, because you can get plus or minus in your a and b's. So I'll quickly put solve that simultaneously on my CAS. So a plus b is equal to 2, and you have x. Okay, so you get these are the options you get. So you get x is equal to -1, y is equal to 3, or x is equal to 3, y is equal to -1. And the only option would be, oh, sorry, not x. Okay. The way I put into the CAS was that this is what it is. And you can see the only option there would be C. Now here's a question where you would have so the next question 2018. So all these white questions you see, these are all from VCAR. So you have a mathematics and a statistics test expressed as percentages. Okay. Okay, they're both normally distributed. The mean of the standard deviation of the math. So I'll say M to be 31. Okay. So M will be maths, and so you have a mean of 31 and standard deviation of 10. And so for statistics, you have a mean of 75 and a standard deviation of 7. Assuming the test scores were independent of each other, find the probability that randomly chosen maths is higher than a randomly chosen statistics. You have maths has to be more than statistics. You have this probability. So let's take a new variable, which is just this one right here. And so now it's just a matter of calculating these. So it doesn't matter if the mean is negative, by the way. Like it will just mean your curve will just be like that, like on this side. So it doesn't really matter too much because of the symmetry. Like if you had a negative mean, it will be here, but if you had a positive mean, it will just be the same. They'll both be the same magnitude. So it'll be the same curve, realistically, just different translation. Okay, so this here, so let's say the expected value of m minus s. So that will be -4. The standard deviation of m minus s would be 100. Let's see, 100 plus. Remember, because you're squaring the -1. So 100 plus 49, and the square root of that. So this will be square root of 149. Okay. Put this into the CAS, so we can get more than 0. The mean would be -4, square root of 149. And I'm going to quickly check my answer. That's correct. Yep, you do. If you put this into the CAS, I'll quickly write my syntax here. So your mean should have been -4 or something else. Standard deviation, you should have been plus or minus -4. Sorry, if you had -4, so let's say your mean is -4. Standard deviation is 149. Then you check probability that minus s is more than 0. Or you could have had your mean as 4. Standard deviation is still the same. But it said your probability would have been s minus m to be, wait, let me see. S minus m to be less than 0. Those would have been either of your syntaxes, but you should go 0.3716, and that answer is B. this one right here. And yep, it is B. Yeah, so the main idea here is really just symmetry, but I will go through it here. So here, which would be like that. Let's see, here would be more like, not the best of drawings, but I will go through. This is -4. Here would be 4. And so standard deviation is still the same. So the graph still has the same width, I guess, or X dilation, I'll put it. And yeah, so if you're looking at less than 0, then that is less than 0, will be this small area. And here, if it's even here, when it's more than 0, so okay, I'll link it like this here. This one here, this one here. And here it will just be this area here. Now I drew it pretty badly, but they are pretty much the same. And you can think of it as they're both symmetrical over this x-axis here. Like if you reflected it over the y-axis, you pretty much get this exact graph. That's really what's happening here. And that's why, and let's say if you multiply by negative, like that's kind of the same thing what's happening here. You're switching the inequality around, and you're pretty much getting the same area overall. I'm not sure how I can explain this any better, but I mean, it should make sense, hopefully. From here, this is where your independent variables come in as well. Oh no, this is still the same thing. Same thing as I said before, where you have another variable to be defined as a combination of two independent. But here it's defined to be that way. It's not defined in this case, like W is not equal to U1 plus U2 plus U3. It's defined to be that way. So you have to use their way of defining it. So U has a mean of 5 and a variance of 1. V has a mean of 8 and a variance of 1 as well. So then you're looking for W is defined to be 4U minus 1. So W is defined to be 4U minus 3V. Whoops. So now in terms of the standard normal, Z, in terms of standard normal, of course, so you're looking at probability that W is more than 5. So firstly, let's find the expected value. So if you have expected value of W, so you have 4 times U, which would be 20. 20 minus 24, which would be -4. Let me quickly check that. That should be, is that right? Yep, that is right. Now you look at the variance. I'll say variance firstly. So 1, 1, that's fine. Now it's 4, so it'll be 16 times 1, which is 16, plus 1 variance, okay, plus 9. So you got 25. So your standard deviation of W is equal to 5. That doesn't look right actually. No, that shouldn't be. 1 second. No, I did something wrong. Let me quickly redo that. Let me see. Your variance 4, okay, 16. No, that should be fine. The standard deviation 5. Okay. So now you have probability of W is more than 5. So we know this formula, so Z is equal to X. Well, in this case, we have W, so we'll probably replace that. Minus mean over standard deviation. So Z would equal 5 minus 4, so it'll be plus 4 divided by 5. So Z is equal to 9 on 5. See? Yep, that's about right. So we look at the probability that Z is more than 9 over 5. And I'm pretty sure this is the same as Z is more than 1.8. So Z is more than 1.8. You got this one here. And be careful not to mix that with this one because it's still, the areas are completely different. Like that's 1.8 and the area they thought here was here. That would be in this option. Well, this is what you're looking for here. The answer should be E. I'm going to quickly check that. Yep, answer E. Yep, so you should have got your standard deviation as 5 and your expected value -4. Next one, here's another defined one as well. So your Z to be defined like this, okay, mean of X is that, and variation, okay. So this is a very simple one. This is from a paper, company paper, so 2 times X, which is 8 plus, was it 9, so 17, and a standard deviation of Z. I'll probably do this much more quickly because, yeah, 4 times 36 plus 9 times by 25. put this straight into the CAS. This should be times by. I don't know why I put plus there. I get 3 root 41. Okay, let's quickly check that. Yeah, so you're going to get 17 and 3 root 41. That was really straightforward. I just realized I didn't even give you the question to do it. Sorry, that's my bad. I'll give you the last one to do. I'll just give you like, let's see, I'll give you like a minute and like 20. Yeah, I decided to do the pink one because it was pretty simple, but yeah, I'll just give you this one to do. With the mean mass of this one. So for oranges, you have a mean mass of 204 and you have standard deviation of 9. You have lemons, which have a mean mass of 76, standard deviation of 3. So you're looking at 3 sets of oranges and 2 sets of lemons. So what you're actually looking at is you're looking at 3 individual oranges and 2 individual lemons. So I'm going to quickly make this easier for myself. I mess myself up there. Let me just quickly. Okay. So we have expected value of this one, which would have been. Let me just quickly go here. So in 3 times with the oranges, so in 204 plus 2 times by 76. That should have got you 764. And then for variance, this would just be, let's see, all that added together. So it would just be 27. Or did I read that right? Yeah, 27 plus 2 times 3, which is 6. So you should get 30. Oh, that's standard deviation. Sorry, let me redo that. Let me get variance first, actually, just to make it easier. So you have 3. So variance of here is 81. Variance here is 9. So 3 times 81 plus 2 times by 9. And we're just getting a square root for standard deviation. Just make that quick here. I think you should get 3 root 29. Just quick check. 3 times 81 plus 2 times 9. Yeah, 3 root 29. And yeah. So that's how you get that one. So did you want me to go through more questions? Or are we like, is that all good?